Hello world, this is Craig. A while back Charles made these boards and I was lucky enough to get one of the early ones. This is the MOD8-9. This is the MOD8-9B. It's Charles's reproduction of the original MOD8-9. Now the original MOD8-9, Charles came across a board somewhere, but he hasn't found any documentation for it. So what he did was he reverse engineered the documentation. He came up with a schematic for the original MOD8-9 and then his version of the MOD8-9B. So what this board does, it's a memory board like our others. Remember, we have our ROM board and our RAM board. Each of these have 2K of memory. This is a combination board. First of all, it has 4K of memory and it's split. There's 1K of RAM, there's 1K of EPROM, and then this chip was originally an 8316, which gave us 2K of ROM. Because of chip availability, Charles had to make a couple of adjustments on this. So the first one he did was the original RAM used to be a 2113, but he changed those to a 2101 because the 2113 they're impossible to get nowadays. The other thing, which is an interesting story that we'll get to in a bit, but this used to be a 8316 ROM, and he changed that to a 2716 EPROM. Okay, so we have a lot more flexibility on that. So let's look at the decoding. What we have to decode is 1K of RAM, 1K of EPROM, and then 2K of this PROM. Here's Charles's schematic for the board. And when we do look at the decoding, let's go back and look at our split octal numbering system. We had N5, N4, N3, and then N2, 1, and 0 for our 6 digits of our octal. N5, which is address 14 and 15, each of those, so we have 4 of those combinations, and those can define 4 16K blocks of memory. N4, which is 11, 12, and 13, each of those would define 2K blocks, and 3 with 8, 9, and 10, those would each define 256 line blocks. Now the nice thing about this MOD9 board is it aligns perfectly with our N5, N4, N3 scheme, and so it makes decoding very easy. First thing we're going to do is let's look at the N5, which is the overall board select. On this board there's 3 sets of dip switches. Switch 1 determines where the 2716 is going to be, or the original 8316. Switch 2 determines where the RAM and EPROMs are going to be, and switch 3 is a address configuration switch. So let's look at switch 3 first. We have address 15 and 14 come in, and those are exclusive ORed with 2 of the switches, switch 5 and switch 4 in bank 3. So with switch 5 and 4, we can decide whether a 14 and 15 are going to be either 0, 1, 2, or 3. And in this case, these 2 exclusive ORs, if you look back at my video that I did, number 38, I think, on the mystery of the magical exclusive OR, we know that this can be used in a few different ways, but in this case, they're using this as an equate detector. So they're basically saying when do these addresses, A14 and A15, match the dip switch setting. When the switch is on, it takes that switch to ground, takes that line to ground, and when the switch is off or it's open, then these pull-ups are allowed to pull these high. So basically the decoding of the overall board, and so we know that it's going to take a 16K block. The decoding goes like this, and the switches look a little bit backwards because on is actually taking it to ground and off is letting it float high. So if we want N5 to be 0, 1, 2, and 3, this is going to be our bit pattern for switch 4 and switch 5. And then corresponding address 14 and 15 will go from 0, 0 up to 1, 1. So that selects the whole board. The next down is this 74138, which is using addresses 11, 12, and 13. That's N4, and it aligns nicely with N4. So that means that this 74138 is creating 8 2K blocks. So we have 8 blocks here that we can select from, and that's what switch 1 and switch 2 are used for. Whenever this switch is on, that means that that will be the 2K block that we're using, and when the switch is off, it means that that's not going to be the one that we're using. So in all conditions, we need to have only one of switch 1 and only one of switch 2 can be on at a time. If we had two of these on at a time, then we would have wraparound and our memory would be selected twice. We could select it at one address, for example, at 0, and then we could select it again if we put an address out at 4 to select output 4. So typically that's not what we want. We typically would only want to have one of these low at a time, so we can use that memory space for something else. Then we have another 74138 that's using addresses 8, 9, and 10, and we can see that's just N3. So this 74138 is creating 8 256 line memory blocks. Okay, so we've got our board select. We then have 8 2K blocks. One of those 8 is used for our 8316 ROM or our 2716 EPROM. And then one of those 2K blocks is used for all the rest of our RAM and our 1702A EPROMs. Okay, well, our 1702A EPROMs, remember, these are 256 lines apiece. We have 4 of them, so that's 1K of memory, so that's half of our 2K block. The RAM, the 2101 RAM, these are 256 lines by 1 nibble wide. So these operate in pairs. So we can see, for example, that this chip select and this chip select down here are connected to the same line. And so these two operate as a pair. This gives us the low byte, or this gives us the low nibble, and this gives us the high nibble. Then these two operate as a pair, these two operate as a pair, and these two operate as a pair. So just like the RAM board, each of these gave us 1 bit of our byte on an output. These guys are selected in pairs, so they each give us a nibble, and so we get our full byte on the output. This is all of our bus drivers that then put this information on the bus. So while we are reserving 16K for the whole board, we can see that these are our 2 enable lines. They come down to this NAND gate, which then goes with our memory read, is NANDed with that. So even though we reserve 16K for this board, we only output to the bus when either our RAM EPROM slot is being selected or when our 8716, 2716 chip is being selected. We can have the mainboard overlap as long as these little 2K blocks determined by A11, 12, and 13 don't overlap. So we just pick this 2K block from switch 1 and that will energize this guy, and we pick a 2K block from switch 2 and that'll energize the rest of these. Now let's look at the lower 74138. This 1 of 8 or 3 to 8 decoder has an interesting little twist. See, they bring in A8 and A9 directly into the 2 lower address bits of this chip, but A10 gets to go the long way. A10 goes through this exclusive OR where it is ORed with the output of switch 6. And in this case, what it is doing is it is inverting A10 depending on the location of switch 6. So if we look at switch 6, well, it's switch 3.6. But if switch 3.6 is equal to 0, meaning that it's on, then this exclusive OR doesn't do anything. We put A10 in, we get A10 back out again. But if switch 6 gives us an output of 1, meaning that it's off, so it's off and it allows this resistor to pull this high, then what happens is we're getting a 1 onto this side of the exclusive OR. So no matter what A10 is, we're getting the inverse of A10, so we're getting A10 bar out. Then that A10 bar comes in and is used for the most significant of the 3 address bits on this 74138. So what does that do? Well, if A10 is just coming in and we get A10 out normally, what happens when A10 is 0, the lower half of these are going to be selected. So if this switch is on, meaning that that's going to be 0, A10 is 0, it's not inverted. So when A10 is 0, these are selected, and when A10 is 1, these guys are selected. So that's A10 equals 0, A10 equals 1. Well, now if we flip switch 6 so that it is off, allowing this to pull that high, allowing this to be a 1 on an input so that this magical exclusive OR inverts, now we get A10 invert out. So what happens is when A10 is now equal to 1, these guys will be selected. And when A10 is equal to 0, then these guys will be selected. So the function of this switch 6 is to invert the order of our RAM and our 1702A EPROMs. So in its natural order with switch 6 on, and so that is set to 0, so this is not inverting, the natural order puts the RAM on the bottom and these EPROMs on the top of our 2K block. So this is the bottom 1K and this is the top 1K. If we switch this and we turn switch 6 off, it flips those over. So now our EPROMs become the bottom half of our 2K block and our RAM becomes the top half of our 2K block. Okay, so that's what switch 6 does in this switch 3 bank. It inverts which of those two are on the bottom. So this is our RAM ROM 2K block selection. And for anywhere from 0 to 7, we would turn switch 2 1 to switch 2 8. One of those would be on at a time, and that gives us whatever the address N5 is, and this is our bit pattern for N4, which is address 11, 12, and 13. We then can change switch 3 6. We can turn it on, which is our natural order. It puts our RAM on the bottom and our ROM on the top. Or we can turn it off, which inverts the order and puts our ROM on the bottom and our RAM on top. So this is then what our completely decoded RAM and ROM looks like with switch 3.6 on, where we have our RAM on the bottom, anywhere from N4 equals 0 to 7, and then repeating with 3.6 off, so our ROM is on the bottom. So that's how we decode our RAM-ROM block, and we can decide which of these we want to be on the bottom. Okay, that's taken care of. Okay, we need to remember in this diagram that this buses are actually connected. So this bus is the same as that bus. Now let's look at this 8316, because that's a bit of a story. This is going to be a 2-minute aside that I hope you find interesting. What we're going to do is let's go back and look at where memory was in the 70s. So let's go to 1973. And in 1973, we had the 1302 ROM. We had the 1602 PROM. And we had the 1702 EPROM. Now remember, the EPROM had just been invented 2 years before this. The 1702 was introduced in 1971. So by 1973, this was most likely a 1702A EPROM, which was the faster version that was much easier to program. So the numbering made sense. 13 for ROMs, 16 for PROMs, and 17 for EPROMs. By ROM, of course, we mean that something was factory masked. So when they made this chip, they laid out in the mask the bit pattern for that entire chip. The PROM, this meant that it was field programmable, but it was one-time programmable. So you would put it in a programmer and you would burn all the little fuses in each of the cells that you wanted, and that would give it its bit pattern. But of course you could only do that once. With the EPROM, we can shine a UV light on it, restore everything back because it has this isolated floating gates, and then we can program it again. So that's where we were. These were all 2 kilobit. That's what the 2 is for. So these were 2 kilobit, and they were set up as 256 lines by 8 bits. Okay, so that's what all of those were. Now in 1975, there was a branding effort, and Intel came out with the MCS 8 collection. This was like the 8008 and all of the chips that went together to support the 8008. And they decided to rebrand these with, instead of a 1 in the beginning, rebrand them with an 8 in the beginning. So the 1702, for example, became an 8702A EPROM. And we had, by that time, instead of the, we had the 8302. So there was the 8302. We now had the 8304, which was a 4 kilobit. We had the 8308 and the 8316, 16 kilobit. However, while Intel decided to do this rebranding with everything at 8, the industry didn't do that. The industry still called this the 1702A. They would call this the 1302, and this was the 2704, 2708, 2716. These were the EPROM version of that. Okay. Now, Intel had a little bit of a problem in that this 8316 was not at all compatible with the 2716, and at this time they were double marking these. They would either come out as a 8316 or it would come out as a 2316. The problem was those weren't compatible with the 2716, so Intel very quickly put an A after this. That was to differentiate it from the E version, which was closer to the 2716. So an 8316E was, you could plop that out and put in the 2716, where the 8316A you could not. So what made this 8308 and the 8316A completely unique at the time? Well, Intel thought we can really simplify systems if we build the address decoder into this chip itself. So what they did with the 8308, it had two inputs. There was the chip select 1 and the chip select 2. Okay, and that meant that having two inputs for the chip select, you could have 4 of these 8308s on the same board with no decoder as long as each of them interpreted these chip selects differently. Okay, so that's what you did. When you ordered up your ROM version of the 8308, you said, and we can look, here's a, this is the catalog, this is the 8308, and we can see in here that when you order this, you're going to submit your mask pattern on either cards or on a paper tape, but you're going to say what you want chip select 1 and chip select 2 to be. And whatever you select for that, there's going to be a little 2-digit number that's written on the top of the chip. So this is the pattern that tells that chip when it's selected. Likewise, the 8316, they went one better and they put in 3 chip selects. So for the 8316, and they also simplified it a little bit, we simply have chip select 1, chip select 2, chip select 3. Those can have any value from 0 to 7. And again, they would have a little 2-digit number on the top. That would be a 06, for example. If that was a 06, that meant that chip select 3 was active high, chip select 2 was active high, and chip select 1 was active low. Okay, so that brings us to answer as to why on this board, this 8316 had 3 chip selects. Here they're all shown as being active low, but these could be any bit pattern from 000 to 111. So anywhere from 0 to 7 would select that particular chip. So now you can see why we had to have some additional logic to select that chip, because when the manufacturer got that chip, let's say they were putting out a system monitor, a resident monitor, or they were putting out a bunch of games or something, and if they had a card that could have 8 of these 8316As, and you could populate that with 8 different games as long as each of those had a different chip select, and they would all be on the same card. There would be no decoding because these chips would individually know when they were being addressed. So in this case, that's why we have to have a switch to determine what chip select 3 and chip select 2 need to be. So when we get this chip, we put it in, we look at the number on the top. If the number on the top is a 6, that meant that 2 and 3 both had to be 1. So we had to set these switches so that 2 and 3 would be 1 to energize, to enable that chip. So we would set switch 1 and switch 2 open, so these pull-ups would then pull them 1. If this number on the top said that it was a 0, that meant that all of these had to be low, so then we would have to close switch 1 and 2, so these would both be pulled low, so chip select 2 and 3 would always be low. So 2 and 3 are always either one way or the other depending on this switch. Chip select 1 went through this exclusive OR gate. So here we take our select that's coming from our 2K block selector. One of these is going to go low. We're going to select this on this switch. So that means that this is going to go low when this chip is selected. So this is going low, but the problem is we may have gotten a version of this 8316 that doesn't want chip select 1 to be low to be enabled. So we have to be able to, on the fly, or using this dip switch, invert that. So this goes low, but if we have to have a chip select 1, let's say that this number on the top said that it was 1, or 3, or anything else that ends in a 1, then this guy has to be operated in an invert mode. So if that's the case, we would take this switch and we would open it up, so this resistor would pull it high, so whatever comes in when this is enabled, it would invert that, so now this is enabled active high. So that's what this logic was for. That's why we had 3 switches here, and we had to have this exclusive OR that was being used to invert, so that no matter what number was written on the top for the chip select pattern, we could match that with this board. Okay, so that's why this had 3 chip selects when it really only needs 1, and that's how this little bit of confusion snuck past Charles. And so on his version of the board, if I can find my schematic for, so on his version of the board, this is why it's a little mistake, and I'm sure he's going to correct this, but he had those 3 connected to the chip enable, the output enable, and the programming line, which when this is a read, I think VPP has to be set to 0. So this one should just be going down to ground. The chip enable can just go down to ground, and the output enable can be connected to this gate right here. So then we can either include this or we can exclude this based on this switch setting. We really don't need that. We could take that out, that gate completely out, but it's already there. It's the 4th one of this, so it came for free. So we can he can decide whether to leave this in or take this out, and that would decide whether or not it would use this switch to include when it's going to be enabled, or that switch would exclude when it's going to be enabled. So a little more complicated if he leaves it in, but it would work either way. All right, so that's a little bit of a side on this, and I guess this story, to finish it up, this whole number with 8000 series, they left that with the closely tied peripheral chips like the 8155 and the 8755 and the 8259, the 8279, and all of those chips, they left that. But for the memory chips, they went back and they dropped the 8000 series and they went to just the 1 and 2. And of course, all this time, there was the 3000 series, which were the Schottky bipolar rather than the MOS version of that. So this is the 78 catalog, and if we look at this in the numerical index, if we look at the 8316A, by now they're just saying see the 2316A. So they're not even including it anymore. They're just saying revert back and look at it somewhere else. This was my first catalog. This was given to me by Dr. Dennis Schwalm, my professor in college, and who got me started in all of this. So a great deal of gratitude to Dr. Schwalm. He taught me a tremendous amount and really got me excited about digital electronics. All right, well, that is what I had to say about the MOD8-9 board, and I'm pretty sure that Charles is going to include this or some version of this document we were looking at that has the decoding blocks in his documentation for that. We'll revisit that if he does the new version and decides exactly how he's going to do this decoding. Okay, so that's it for the MOD8-9 board. I'm excited to build mine, and if anything comes up when I'm building it, I will let you know, but I appreciate you watching, and I hope you found it interesting. Bye-bye.